In the last episode, we look at the blueprint. Today we pick up the tools. Building an operating system isn't just about the writing a code, it's about the creating an environment where that code actually exists. When you write a normal app, you have an OS to catch you if you fall. Here there is no safety net. If we make an mistake, the computer doesn't show an error message. It simply vanishes into the triple fault reboot loop. Today we are going to build our factory. It means our operating system, sign a contract with a bootloader and see the first spark of the life from an CPU. So it require, before we start the hammering away to code, we need to organize our headquarters. When you build something as a massive as an operating system, you can't just throw all your files into one folder. We need a structure. So for this, here is the how we are organizing our project. The first is our src folder. It means our source directory contain the boot folder. This folder, it is this like the ignition room. What exactly ignition room? These files are written entirely in assembly language. Their only job is to talk to the hardware the millisecond the computer turns on, set up the absolute bare minimum and pass control forward. Then another file is a kernel file. As our source directory there is a kernel folder. This is the brain of our system. Everything here will be written in the C programming language. This is where the actual logic of our OS lives, handling memory, drawing to the screen and reading to the keyboard. And then another folder is a include directory contain kernel folder. What is exactly difference between source directly contain kernel and include directly contain kernel? This is our blueprint. In C, you use the .h. It means header files to tell the different parts of the code how to talk each other, and another file which is a make file. Finally, sitting right at the root of our project is a factory manager. Instead of typing long complex command to compile 100 different files, every time we make a change, we write the rules in one file. We just type make and this file automatically builds our entire operating system. By keeping our ignition, our brain and our blueprint separated, our project will stay clean even when it is grow to the thousands of lines of code. But to actually build this file, we need to write the news. Before we cook, we need to write news. We can't build the operating system with a standard compiler, because standard compiler assume an OS already exists. So then try to talk to libraries like stdio, std library that simply aren't there yet. We are the ones who have to write those. So we are setting up our tool chain. This is our specialized shift knives. First is a standard compiler. Assume OS already exists. So we try to talk libraries, because we writing talk libraries like stdio and stdlib, because we are currently using the C language as in writing a kernel. So we are setting up our tool chain. First is a NASM, then GCC and LD, and another is a KEMU. What exactly these three things? NASM is our translator. If you heard about the translator, it means this is our specialized for the assembly language programming. Assembly language programming. It means ALP. It turns our human readable CPU talk into a raw machine code. It's the tool that handles the very first heartbeat of the system. and another is a GCC and LD, which is the master builders. It is the master builders of our system. GCC takes our C code and turns into a blocks. Then LD, it means our linker, acts as the architect. It take all those blocks, the assembly and the C, and links them all together into a single precise file, which is called the kernel.bin. Its tool then handle the it basically takes all those blocks and assembly and C and links them into all together into a single precise file, which is a kernel binary file. And another is a KEMU. This is the most important tool for our sanity. Instead of the risking our real hardware, we will run our OS inside the powerful emulator, which is a KEMU. KEMU is a emulator which we'll be using currently. If you are using the Linux system like the Arch, it takes just one command using a pacman package manager, and our factory for the open to business. What is the basically command? Sudo pacman -s base devil and nazam, which is our translator, and KEMU system x86 or a group, and libisubun mtools. It is a command which can use in the Arch for installing these all dependencies. If you are using the Debian based Linux operating system, so you can easily install sudo apt install. Likewise, so I am currently using the Arch Linux, so I will executing the command and install the dependencies. Sudo, 1 second, I will attach my mic. So sudo pacman base devil and our transcriptor, which is a nazam, and emulator KEMU system. We are building the x86 using the x86 architecture, and group, which is our bootloader, and libisubun mtools, and was just entering my password. Okay, it will install. Then the very first file we need to write, which is a header.asm. This is our contract with the bootloader. When groups loads our OS, it scans the first few kilobyte looking for a magic number. So what exactly is the magic number and what does the header.asm file do? We will check that. Initially, we will make our project structure file. Make directory SRS, which is a source directory, and inside the source directory we need to create two directories. First is a boot, source boot, and another is a kernel directory. We already discussed about that. And also one most important directory, which is the include kernel directory include, and inside the include kernel. Okay, we will start our writing the code from the header.asm inside the source directory, and boot header.asm. So header.asm, the code will start from we will writing the code in the assembly language programming, and this code will start from the section section dot multi boot header. What is does exactly section dot multi boot header? This is a tags, this code, so the linker script knows the put it at the very top of the file. Then header will start. In the magic number, it means our multi-boot 2. It is a comment in the assembly language programming. And DD, what does exactly this magic number? It is the address E85250D6. This is the magic number for the multi-boot. When group see this, it recognizes the file as a modern OS, because we using the multi-boot 2 inside the architecture. 0, it is our protected mode. For the protected mode, I6, and the protected mode will be the DD0. It is the address for the protected mode, and another is the address for the checksum. DD 0x100 -O 0xC85. These are the basically addresses to write the correct checksum. 0 D6 plus 0 header end minus header start. Then frame buffer. What exactly frame buffer does? Frame buffer request align it to 8, and DW, it is a command in assembly language programming for the data write 5 type. DW 0 flags 0, it means require. Another is the DD, it is a size DD1024, DD786. Size will be width and height. 32 is the depth, and in tag align with this 8, data write 0, DW0, DD8, and header will be end. In this program, there is a DD0. DD0, it sets the architecture to the standard 32-bit x86 protected mode. It means we are currently building the OS which will be running on the 32-bit x86 architecture, and DD header end and DD header start, DD header end minus DD header start, it can calculate the exact size of the header block, so group know where it ends. And another is a checksum. Checksum, which group adds the magic number, architecture, length, and this checksum, the result must be 0 for the boot to proceed. this frame buffer tag, we request to 1024 into 768 screen with the 32-bit color before the OS even starts. Save it and going for the another target. Now we write the main.asm file. This is where the CPU takes the first breath and the bootloader has done its job, and now we are in control. We start the 32-bit mode. Going to the SARC boot main.asm. Here global start, it starts from the global start, and extern long mode. We will check what exactly long mode, and the section initially text and bits, which is 32 bits, and start CLI, then move ESP, and stack top of the stack initially move to the ESP, and move this ESP, EDX. This is our another register, EAX, and move ESI to EBX. Then our VGA marker will start. Move dword 0xb and 0 to 0x4f 314 f31. This is exactly the address, and we will move this address in the data word into 0xb800. We will check in and compare this with EDI to 0x36 D7 6289 and JNE no multi boot, and call the subroutines. First is a check CPU ID. We will write this CPU ID, then call the check long mode. What is exactly long mode? We will check that. Then call the setup page tables, then call the enable paginning, LGDT GDT 64 pointer, then jump GDT global descriptor table 64 dot code to long mode start. We will understand this line by line. Initially, it means there is a bit 32. It can generate a 32-bit machine code. The bootloader always start with a 32-bit mode, and then another is a CLI. It means clear interrupt. It is a clear interrupt flag. Tells the CPU to ignore hardware signal like a keyboard presses while we are setting up, and then move this our stack top of the stack into a ESP. It means we are initializing the stack. Without a stack we cannot use call and push instruction. And here is a move dword, directly writes to the VGA text buffer. 0x4f is the red background, and 0x31 is a basically 1. And here is a compare EDI, verify the secret password left by the group in the EDI register. And here is the LGDT, which can loads the global descriptor table, which define the memory rules for the 64-bit mode. and jump into the 64-bit mode. It means global descriptor table of the far jump that switches the CPU. Initially CPU bootloader start with a 32-bit mode, and then after we jump into using the global descriptor table, switches to CPU into 64-bit long mode. One twenty.
अभी खाली कितना है?
54.
54. तो हमने को स्लो करना है अभी के लिए।
And
इसको इतना कर देना फिर।
so we have our assembly files, but how do they fit together? We need a map. This is our linker script. To mapping these assembly language codes, we write the linker script in the root folder of our operating system, linker.ld. It will start with the entry start and sections dot 1m. And go to the kernel start and dot boot multi-boot header. And then dot text dot raw data dot raw data dot data dot bss dot bss and kernel will be end at this point. We understand the exactly line by line. There is initially start with the entry start. What exactly tells it? Tells the linker that the very first instruction of the OS is a start label. Then section in the under the section there is a dot equal to 1m sets the current address to 1 megabyte. This is where the OS will be loaded in RAM. Then kernel start which can save the starting address into a variable we can use in C later. And then dot boot, it can forces our bootloader contract to very first thing in a file. And dot text dot raw data dot bss that stacks our code constant variable empty memory buffers in a clean organized layout. And the last one is a kernel end. It can mark the exact address where our operating system end in a memory. This is our linker.ld. Then we will start to write our next file, which is inside the source folder, boot folder, which is also one of the important file, the long mode init .asm. This is it. We made the jump. We are now the long mode init ASM. What exactly this assembly program or this assembly file does? It can initially we in main.asm we start with a global start. In this file we will start with a long mode start and then extern kmain and going to the section.text. It will call the bit 64 bit and long mode will start using the register. First is the move register, we are using AX at 0, then move this AS into SS, and then another AX into DX, then move ES into AX, then move FS, move AX into FS, then move AX into GS. Then VGA, it means OK, in a light gray on a black. You can move racks 0x, 0f, 4b, 0f, 4f. Move 0x, b, 8, 0 into RAX, and call the function which is a kmain and halt it. What exactly is this code? Notice the bit 64 at the top. It means we did it. We are in the 64-bit highway. The first thing we do is the cleanup the old 32-bit data register by setting them to the 0. Okay, we don't need them anymore. To prove we made it, we are going to write a OK to VGA buffer, and we then call our C kernel, it means our kmain function, and halt the CPU. So in this episode, we have successfully seized the control of our hardware, passed the bootloader's checks, and forced the CPU into 64-bit mode. In the next episode, we cross the